Alright, so continuing lecture 12, we'll talk about calculus on M. In particular, I want to talk about how do we, differentiate with respect to U and V. Well, it's not, I'm not quite going to sell it as that just yet, actually, but eventually it becomes that. Anyway, so we're dealing with a patch, all right, and so we want to talk about x of uv, y of uv, z of uv. So this is the component functions of the patch, right? And so if you think about that, you can think about the parameter space uv, right? And through a particular point, and so that we have the patch takes us from there over to the surface, right? And I'll just, I think about this as being a simple surface just for the sake of discussion, right? Anyway, there's some point here, say u naught v naught, right? That maps you over to some point P, right, where P is equal to x of u naught v naught. And then we can consider horizontal and vertical curves in the parameter space. So a horizontal curve, something like this, right? And so a point on that curve would be something like u comma v naught. In other words, v is equal to v naught on that line. That gives me some kind of curve over here, right? Which we'll call alpha. So this point over here would be, say, alpha of u. So to be specific, alpha is defined. How is alpha defined? Alpha of u is by definition x of u comma v naught for the current discussion, right? And the vertical direction, like this, well, point on that line would be something like u naught comma v, right? And the image of that vertical line under x gives me some other so-called coordinate curve over here. These are the u and v coordinate curves on the surface, x of d. So again, you can do this locally if the surface is not simple. You can do it at each point. And so that point, I would say, would be beta of v. Now beta is the other coordinate curve, say beta v. So alpha I'm using for the moment as my notation for the u coordinate curve, beta the notation for the v coordinate curve on the surface, and beta would be x of u naught v, like that. Now you can then define partial velocities on the surface in terms of tangents to these curves. So let's see here. For alpha, if you want me to picture, I can picture it, the velocity as if it's attached there like that. That would give what's called x u of u naught v naught. And then up here, we'd have x v of u naught v naught. And by definition, all right, we have the following. So xu of u naught v naught is simply equal to alpha prime of u naught, and xv of u naught v naught is equal to beta prime of v naught. But to be more explicit about it, this is really what? This is really ddt of x of what? Of t comma v naught, putting t equal to u naught afterwards, and this is ddt of x of u naught comma t, setting t equals to v naught after the differentiation. Now, but, let's be clear, these are velocity vectors, which means that they're derivations you know, understood as vectors in the tangent space to P of R3, okay? Which means that technically speaking, they're derivations. Let me be more explicit about that. Let's see here. So XU would be equal to, and this is all at the point, oh fine. The point dependence here gets kind of old. Remember XYZ up there, so this is really ddt of x of t comma v naught. Do that differentiation, you set back t equal to u naught at the end of it, but this goes in the u1 direction, and technically speaking at the point P, okay? And likewise, ddt, after the differentiation is done, you evaluate t equals to u naught. That's the y of t varying v naught is frozen, that differentiation, right? And then that goes u2 of p ddt z of t comma v naught set t equal to u naught after the differentiation, u3 of p, where you'll remember that u sub I of p is actually equal to partial x upper I at p, right, to be more careful. Now, the chain rule, right, the chain rule on this, just to unwrap it further, this guy right here, if you look at ddt of x of, let's say, t comma v naught, well, that's equal to partial x partial u, well, du dt plus partial x partial v dv dt. But here u is equal to t and v is equal to v naught, so this just becomes dt dt, which is 1, and this is 0. And of course, to be more specific, it's really partial x partial u at the point u naught, v naught, supposing I eventually set t equal to u naught at the end of it, right? So let me summarize our results in the next page. It's very natural. It's kind of what you'd expect from the notation. Let's see here. So what we have then is x sub u is really equal to partial x partial u u1 plus partial y partial u u2 plus partial z partial u u3. If I had more sense, I would probably just made that the definition and not bothered to try to motivate for you how that came from the curves we were talking about. After all, this is actually how you calculate, but that's not how we operate, so here it is. All right, so that's basically what comes from the chain rule in our study on the last page. Now, let's see here, what else should I tell you? So O'Neill actually calculates these for the sphere. I'll let you read that. I'm not going to do it here. We can use these though to return to the question of regularity, right? So, but first a definition. We've been using the term patch. We can also use the term parameterization. The difference between a patch and a parameterization isn't much. Well, maybe it's a big deal. It depends on your preferences, I suppose. A regular mapping, x from D to R3 with x of D, a subset of M, is a parameterization of the region x of D and M. So you notice that we assume regular, but we do not assume one-to-one. Now, advanced calculus tells us that regularity actually gives us that the function x, mapping x, is locally injective. In other words, if I was to take the domain D, chop it down smaller, I could get the restriction of x being injective on that smaller set. But we don't insist that it be injective on the totality of the domain here. A parameterization might come back to where it started, for example. Now, so what is regular again? Let's pick on that. So regular means that I told you it meant that the rank of the Jacobian of x was equal to 2 everywhere, right? So to be more explicit, that means that if we look at the Jacobian of x, which is equal to, what is it? It's well, it's this matrix partial x partial u partial y partial u. Look familiar? Partial z partial u. Second column partial x partial v partial y partial v partial z partial v. So in other words, if you convert these two, it's just their column vector equivalents. Basically, it's slight abuse of notation here, folks, but it's essentially xu, xv. But because I'm feeling guilty in being pedantic about it, let me just stick a vector symbol of this. I forget if I had invented special notation in the last part of the courses or not, but again, these are the column vectors, right? They're not derivations when I write it this way. I'm just thinking about the linear algebra of it. So the rank is 2 if these are what? Linearly independent. Let's see, other ways you could express it. If you look at this as you've got a 3 by 2 matrix, right? There are a couple different ways you can capture that. I think when I took differential geometry, we looked at these. Oh, I'm sorry. Call you back. We looked at these 2 by 2 submatrices, and so if the determinant of that 2 by 2 matrix was if any one of the 3 possible 2 by 2 submatrices had non-zero determinant, that gave you regularity. In retrospect, that's a really, I don't know, I'm not a fan of this actually. It's kind of awful. More to the point though, in terms of Calc 3, we can calculate the cross product of xu and xv, right? The cross product, and if this is not equal to 0, then that implies that xu is not parallel to xv, right? If xu and xv are collinear, if you think about them as geometric vectors, then they would be linearly dependent, and the rank of the Jacobian matrix here would not be 2. So you've got these different ways of looking at it: linear dependence of the Jacobian matrix, columns of the Jacobian matrix. you could look at these three, any one of these 2x2 determinants taken from the submatrices here being non-zero would also give you linear independence of the column, rank 2. The condition we often use in this course, and typically a definition, you'll see in other books, regular surface being one for which it has patches, and the patch has to satisfy this condition. This condition also gives regularity. In a convenient format for students to recognize, right? Not everybody's had linear algebra, so these other ideas are not as familiar. So let's see here. With that, I'll let you, oh well, there's a few other special surfaces he talks about. Ruled surface, he talks about a torus. Again, the geographic patch on the sphere, I'll let you read those. I'm going to move on here to section 4.3. I'll make that the next lecture since someone just called me and I have to call them back. Sorry for this being so chopped up. Thanks.